Welcome back everyone. In the last lecture we found out how to get to an input by which we can reach from 0 to a final state. It might not be always possible for us to reach the final states. Okay. If the system is controllable, we know that we can reach from 0 to any arbitrary state and we can find out inputs for that. To find out the inputs, we had used the idea of controllability Gramian and we had solved the linear equation W t eta equal to x bar, where x bar is the point which you want to reach from 0. Today we will try to characterize the points or the states which can be reached from 0. Till now what I have said is a definition which says that okay, I can reach from 0 to particular states. If I can reach all states from 0, then the system is controllable. But if suppose I cannot reach all states, which are the states I can reach? Is there a way of finding that out? Even we can also ask the question, is there a way of finding out whether I can reach all states just by looking at the system equations? We will look into that today. So, remember this was what we did in the last lecture. This was the main idea. Now notice this. Suppose I take WTF eta equal to x bar t. Okay. Now, to get an input u tau, I need the value of eta, and to get an eta, I will need to solve this WTF eta equal to x bar. So, if I have to solve this WTF eta equal to x bar, remember this is like Px equal to q. I am trying to solve this set of linear equation. When is this set of linear equation solvable? One option was that rank of PQ must be equal to rank of P. The other way of formulating the same thing was that Q must belong to the image of P. Remember we had talked about this. So, basically I should be able to write down x bar as linear combination of the columns of WTF. If I can do that, I know that this set of linear equations is solvable, and once I get a set of linear equation, I can go ahead and find out the input. Now, that means, what do you think that means? That means the reachable states or the controllable states must be in the image of WTF, right? Because for this equation to be solvable, I know that x bar must be in the image of WTF, then only this becomes solvable. Okay. And therefore, x bar, the reachable states must be, or the controllable states must be in the image of WTF. Now, if I define the set of reachable states as this, say RTF, I use this symbol, RTF equal to the set of all the states that you can reach in some time, then you can see that image of WTF must be equal to RTF. Let me try to explain it to you with the help of a diagram in R2. Suppose you have x dot equal to Ax plus Bu, where you have only two state variables. So, the state vector is of size 2 cross 1. If the system is controllable, you will be able to go from this origin 0. So, this is 0 comma 0, right? This point to any point in R2. Remember, what are these points? What are these points? If I say this is A, B, A is a state variable, B is a state variable. Okay, you can think of it as the RC circuit that we had taken in the last lecture. So, say A is VC1 and B is VC2. So, I can go from 0 voltage initial condition to some voltage initial condition, some final condition AB, okay, using some input. If the system is controllable, I will be able to go to any point in this entire space. Okay. However, if the system is not controllable, then I might not be able to go to any point on the entire space. I will be able to go to only those points which belongs to the image of WTF. Now, what is image of WTF? Image of WTF are nothing but the span of the columns of WTF. So, I might be able to reach maybe only a part of the R2 plane. Okay. So, in 3D if you have to draw this, it will look something like this. Suppose you are in R3, then maybe you will be able to reach only this plane or any other plane which passes through the origin. So, the point that I am trying to explain is that the parts which you will be able to reach can always be written down as the linear combination of the columns of the controllability Gramian. Okay, I have not rigorously proved this lemma, but I am just giving you the intuition as to how this works. So, let us carry out this thought experiment. Let us consider that the system is controllable, fully controllable. You can go to any point from the origin. What can we tell about the image of WTF then? Since you can go to any point, the image of WTF should be equal to Rn, right? Think about it in this way. Suppose that example, R2 example that we took, RC circuit, suppose you have two capacitors. So, then in that case what we are saying is that you can go from 0 to any voltage that you want, any final value that you want. So, that means I will have to solve WTF, eta must be equal to anything that I give here. Okay. Now, when will that be possible? That is possible only if you can WTF here becomes invertible, because then I can solve eta equal to WTF inverse of this. So, the image of WTF must be equal to Rn, and in other words it also means that controllability Gramians, each column here should be linearly independent with each other, because there are n number of columns. So, if image of WTF has to be equal to Rn, then all the n columns here must be linearly independent to each other, which means the rank of the matrix must be n. So, this is what is being said here. A system is AB controllable. So, this is the way we tell that a system is controllable. We say AB controllable. Okay, a system is AB controllable means a system is controllable basically. Okay, this is just a way of telling. A system is controllable if and only if the controllability Gramian is non-singular for all t greater than 0. Because see, again remember what we are trying to say. We are saying that you find out Wt, right? Now, the Wt depends on 0 to t. Here it depends on the value of t that you give. Okay, what we are saying is that a system is controllable irrespective of whatever t you give. Doesn't matter. You give any time, doesn't matter. Wt will always come out to be non-singular. Remember, Wt is a constant matrix, right? Because I have done the integration and the definite integral I have put into the matrix. We saw that example, right? So, in that example we had done that previous lecture. So that when we put the definite integral, it became a constant matrix. We are saying is that whatever value of t you put, okay, doesn't matter. Wt will always come out to be a non-singular matrix. Okay, if the system is controllable. If the system is not controllable, it will not be true. But if the system is controllable, this has to be true. Okay. Again, see, I am skipping the proofs here. Okay, there are lot of involved proofs here which can always be done, but I am skipping the proofs here. You try to understand the idea. Okay, WTF was generally used for finding out the inputs that will take me from 0 to some point. Okay, in any arbitrary time. If the system is controllable, I can go from 0 to any point. So, that if that is the case, then Wt must be invertible at any time you give, okay, for the system to be controllable. So, these two statements are equivalent to each other. If you can show that the controllability Gramian is invertible for any time you give, then the system is controllable. If the system is controllable, then the controllability Gramian will be non-singular. Okay, that is what is being said. And one important thing is that image of the controllability Gramian is the controllable space. Okay, so the places where you can reach is given by image of WTF. Okay. Now, you see, this is well and good, Okay, fine. I found out, I started this lecture with this idea, right? How do I know where can we reach? Now we know which are the points we can reach. Which are the points we can reach? Image of WTF. Any vector which is in the image of WTF. Again, remember what is image of WTF? Linear combination of the columns of WTF. So, any vector in the which can be written as linear combination of the columns of WTF is a controllable state. Okay, and those are the states which I can reach. I have characterized the controllability space. But you can see that finding out WTF, doing this integration, it is a bit it is involved, right? It depends on time, so you have to do this integration. So it is involved, although it helps us to find out the input, of course. Okay, but it turns out that there is an easier way to find out which are the points you can reach, and that is given by what is known as the controllability matrix. The controllability matrix of a system is defined as this matrix: B, AB, A square B dot 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 A to the power of n minus 1 B. Remember, our system is x dot equal to AX plus BU, right. So, using A and B, I can create this matrix. Now, what is this matrix? This B is an n cross m matrix. This AB is A is an n cross n matrix, B is an n cross m matrix. So, total this is an n cross m matrix. This is also an n cross m matrix. So, as a whole, you can see that this is some kind of a fat matrix. Okay, it is not a tall matrix. So, there will be the number of columns are much higher compared to the number of rows. Of course, if it is a seesaw system, then M is 1. If it is a seesaw system, then the controllability matrix is a square matrix n cross n matrix, because M is 1. Okay. But if it is not a seesaw system, it is a MIMO system, then the number of columns are higher than the number of rows. It is a fat matrix. Okay. Now, it turns out, okay, that the image of CAB, again this is a matrix, right. Since it is a matrix, we can talk about all the 4 fundamental subspaces that we had talked about in the linear algebra lecture, right. So, since it is a matrix, I can talk of image of CAB, image of this matrix. So, it turns out that the image of this matrix is equal to the image of the controllability Gramian, which in turn is equivalent to the reachability set or the controllable states, set of controllable states. So, you see, this has given us a very easy check, right. Previously, we knew that image of WTF equal to RTF, RTF being the set of all states which are reachable, or the set of all controllable states. Now, we are saying that no, image of WTF is also equal to image of CAB, okay, where CAB is defined like this. CAB is controllability matrix is defined in this way. Now, you see, finding on CAB is much easier, no integration, nothing, just multiplication, B A B square B, and then you have to find out the image of this, that will be nothing but the reachable set. Let us see why this is true. This looks quite weird, right? Think about it. WTF was found out by integrating from 0 to TF and doing all these type of integrations. It depended on time, right? Whereas CAB does not even depend on time. It is B A B square B. And we are claiming that the image of this controllability Gramian is equal to the image of CAB. So one which was dependent on time and the other is not dependent on time. So, the reason, so why I am telling you is that controllability actually does not depend on time as such. Basically, if a system is controllable, it will be controllable for whatever time you give. That is what the idea is. Okay. If a system is controllable or a state is controllable, it is controllable for any time you give, does not matter. Okay. So, the image of, so the controllable states are given by the image of CAB. Let us see at least some idea as to why this is true. Okay. Again, some intuitively only I am going to explain. So, suppose x1 is in the image of WTF. Okay. If x1 is in the image of WTF, we know by this lemma that x1 is the reachable set, reachable states. Now, what is a reachable state? Reachable state is any state which is reachable from 0. So, from 0 to that state I can reach, that means I can find out a UT that will take me from 0 to that state. Okay. So, from 0 I can go to x1, which means that there is an input here, so which has to satisfy this equation, because where is this equation coming from? This is coming from this equation. 0 to t e to the power of a t minus tau b u tau d tau, this is coming from this equation, but here this part is 0. So, we have x t is x 1 here. So, this is what I am writing, x 1 equal to 0 to t f this. Okay, this is true. Why is this true? Because x 1 belongs to the set of reachable states. So, I can always find out an input, say u t is that input. So, that must satisfy this. Once it satisfies this, notice that this is e to the power of a t, e to the power of the matrix exponential can be written in this way, right, and that is what I am writing here. You see this is the matrix exponential part, series expansion of e to the power of a t f minus tau, t f minus tau is your t in this case, say. So, therefore, I can write it down in this way. Now, once I can write it down in this way, now here is the thing that we know that A satisfy the Cayley-Hamilton theorem. So, if chi of S for A is A naught plus A 1 S dot 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 A to the power of n minus 1 S to the power of n minus 1 plus S to the power of n, then we know that chi of A is equal to A naught I plus A 1 A plus dot 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 A to the power of n minus 1 A to the power n minus 1 plus A to the power of n, right. So, on the left hand side this will become 0 due to Cayley-Hamilton theorem. So, now I can write A to the power of n as some combination of my I A square and dot 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 up to A to the power of n minus 1. So, which means here notice in this expression, although k is going from 0 to infinity, at k equal to n, this becomes A to the power of n of b, but A to the power of n of b can be written as again linear combinations of I A square to A to the power of n minus 1. Similarly, if this was k equal to n plus 1, this would have become A to the power of n plus 1 b, but that can be written as A to the power of n into A to the a b, but A to the power of n can again be written in this way. Okay, there you will get another A to the power of n term when it multiplies with a b. You can again replace A to the power of n by this. So, basically the point being made here is that this infinite series is not actually infinite. I can rewrite this series in terms of powers of A to the power of 0 to A to the power of n minus 1. Okay, in terms of A to the power of 0 to 0 b to A to the power of n minus 1 b. So, I can rewrite this expression in this way. But what is this? Notice what is this? This is nothing but alpha 0 T f b plus alpha 1 T f a b plus dot 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 alpha n minus 1 T f a to the power of n minus 1 b. But this expression can also be written in this way. See this expression, this multiplied by this. So, that means you see what is x 1? X 1 is nothing but the linear combination of the columns of b, a b up to A to the power of n minus 1 b. So, x 1, what was x 1? X 1 was a reachable state. So, a reachable state is being written down as linear combination of b, a b, a square b, and that is the reason. Again, this proof is half, actually you have to also show another half, but in general you understand the idea that the reachable state can be written as linear combination of the columns of b, a square b up to A to the power n minus 1 b. Okay, and that is the reason x 1 will belong to image of CAB, and the other way around can also be shown that if x 1 belongs to image of CAB, then x 1 will also belong to image of WTF. That is the part I am skipping here, but just to give you an idea, I showed you this half proof basically. Okay. So, what we are saying then is that you see image of, first of all, what is the set of reachable, what is the set of reachable states? This is the set of reachable states. Okay, and the same state can also be represented by image of WTF. So, basically you take any point here that can be written as linear combination of the columns of the controllability Gramian. It turns out this is equal to image of CAB, which means you take any point here that can be written as linear combination of the columns of CAB. WTF is an n cross n matrix, and what is CAB? CAB will be a n cross n m matrix. Okay. So, you can see that this is a fat matrix, this is a square matrix. Okay. So, but the image of both these matrices is the reachable set. Now, like for the controllability Gramian, we say that if the system is controllable, then this controllability Gramian here must be non-singular, right, must be non-singular. In the same way, if AB is controllable, then of course image of CAB also should have full rank. Okay. In other words, see, remember this is a fat matrix again. How many number of rows? N number of rows and nm number of columns. So, the maximum rank this matrix can have is n, not more than that. Okay. So, the rank of this matrix, the maximum rank this matrix can have n, and it turns out that if the system is controllable, the rank of CAB must come out to be n. Okay. So, these three statements are equivalent to each other. If you show that rank of CAB is n, then also system is controllable. If you show that the controllability Gramian is non-singular for all time t, then also the system is controllable, and in general if a system is controllable, these are the two conditions which are equivalent to each other. Let us look at this example RC circuit that we had taken. This is your RC circuits that we had, and this was the state equation that we got. Now, if I have to ask whether this system is controllable or not, one way is that you can find out the controllability Gramian WT and see whether it is whether WT is non-singular or not. Okay. But an easy way of checking this is going for the controllability matrix. What was the controllability matrix? Controllability matrix was BAB A square B A to the power n minus 1 B. Okay. In this case, n is 2. So, which means this will be B and AB, only these two factors. Okay. So, this is your A, this is your B. You can easily find that out what is B and AB. A multiplied B will be this column, and this is your B. Okay. And from here, can we say that the system is controllable? Now, for the system to be controllable, we know that the rank of CAB must be equal to n, but n in this case is 2. For the rank of this matrix to be 2, we know that both these columns must be linearly independent to each other. Good thing is that this is a 2 cross 2, this is a square matrix. So, when will the rank of this matrix be 2? If the determinant of CAB is not equal to 0, okay, then only the rank of this matrix would be 2. So, you can find out the determinant of this, and the determinant of this will be not 0 only when R1 C1 is not equal to R2 C2. If R1 C1 is equal to R2 C2, you will see that the rank of this matrix will be less than 2, and in that case we will say that the system is not controllable. Let us take some numbers here. Okay, I am replacing R1 C1 and R2 C2 with some values. This is the state equations that you will get, and then if you find out CAB, this is the controllability matrix that you get, and the system is unreachable or uncontrollable, both are the same thing. Uncontrollable, the system is uncontrollable here. Okay. Now, I can always ask, okay, the system is uncontrollable here, that means I cannot control some of the states. Okay, what is the meaning of that? I will come to that, but I can always ask, okay, fine, then if I find out the image of CAB, that will give me the controllable space. These are the points which I can reach actually. Okay. So, what is the meaning of these two points? Okay, let me try to emphasize it with the help of this circuit. Okay, so when I say that 1 alpha is reachable, that means I can go from 0 0 to any value of 1 alpha, where alpha can be any number. I can go from 0 0 to 1 alpha in any time that you give. I can always find out an input V here that will take me there. But if it is not in this set, okay, if it is not in this set, then I won't be able to do that. Okay. So, for example, let us take this question. Find input ut such that the capacitor voltages are 2 volt each at 1 second if initial capacitors are discharged. So, initially the capacitor voltages are at discharge, which means they are at 0 volt, and I want them to be at 2 volt each, okay, at within 1 second. So, I want that they should be at 2 volt each within 1 second. Now, if I have to check whether this is possible or not, I can quickly go ahead and check image of CAB, and I know that the image of CAB is nothing but image of the matrix 1 1 minus 1 minus 1, right, and I know that you see 2 2 belongs to the image of this matrix, because 1 1 minus 1 minus 1, if you want to solve this expression, okay, you can always give here 2 0 and you will get a solution, right. So, that means 2 2 can be written as linear combination of these two vectors, two columns. So, 2 2 belongs to the image of this matrix, okay. 2 2 can be. So, basically what do I mean by 2 2 belongs to the image of the matrix? Again I am repeating, if you take this matrix 1 1 minus 1 minus 1, I can find out a value of A1 and A2 here such that this equation is solvable. Then only I can say that this is in the image of this matrix, okay. Now, in this case 2 2 is in the image of this matrix. So, therefore, I can go from 0 0 to this point, okay. I can find out an input. Let us see. So, you remember how to find out inputs. We had already seen this from the Gramian perspective. Input can be found out in this way. So, this is 2 here. So, input can be found out in this way, okay. So, we will try to find out the controllability Gramian. So, if you go ahead and find out the controllability Gramian, this is the controllability Gramian that you will get. Go ahead and solve it. You know how to solve it by now. So, you have to solve for W1 eta equal to 2 2, right. This you can easily solve, because what is W1 eta? You can see from here that if I take this as the W1, so this becomes 0.5 minus 0.5 e to the power of minus 2 1 1 1 1 eta equal to 2 2, right. If you try to solve this, there can be many solutions to this. One of the solutions will be eta is equal to 1 1 2 by 1 minus e to the power of minus 2, okay. So, this will be a solution. So, once you have eta, you just have to plug it in here to get the value of ut, okay. Now, if the problem has been changed, instead of 2 volts at 1 second, if I want something else. So, now suppose the problem has been changed to this, that I want the final voltages to be 2 volt and 1 volt, here 2 volt and here 1 volt, okay. In that case, the controllability Gramian is this. Similarly, the controllability Gramian remains the same, only thing is that the right hand side now becomes 2 1, and you can see that 2 1 is no way in the image of this matrix, okay. This is anyways a scalar, right. So, I just have to look at this matrix. The image of this matrix does not have 2 1, this will have no solutions. So, you will not be able to take the voltage of this system from 0 0 2 to 2 1 within 1 second. As a matter of fact, even if you give any other seconds also, it will not be able to solve this problem, because you see the right hand side has a 2 1 which is not in the image of this matrix. So, now notice that 2 1 is uncontrollable, right. 2 we have already seen 2 1 cannot be controlled. You can directly also see it from the image of CAB, okay, because the image of CAB is nothing but, again we had already calculated this, the image of CAB was this, right. So, 2 1 is not in the image of this matrix. So, 2 1 cannot be controlled, that means it cannot be taken from 0 to 2 1, or so in the same way 0 1 is also not in the image of this matrix, 0 1 cannot be controlled, okay. However, notice that if I add these two up, I get 2 2, 2 2 can be controlled, right, because we saw a problem where we can find out an expression of eta, we can find out a vector eta that will solve this problem. So, what the point that I am trying to make is that if you take two uncontrollable states and you I mean it is possible that even when you add them up, you can get a controllable state. However, remember, if you have a controllable state, if you have suppose two controllable states, okay, you know that the controllable states are from image of CAB, okay. That means, what is image of CAB? Image of CAB is a subspace, it is a vector space, right. The controllable states are in that vector space. So, if you take any vector, any two states which are controllable, and add them up or scale them up, or take any linear combination of them, the new vector that you get will also be in the controllable space, because it is a vector space, right. Image of CAB is a subspace which is a vector space. Vector space property was that it is closed under addition, it is closed under scalar multiplication. So, controllable space is, that's why I have been always telling controllable space, okay, whether you noticed it or not I do not know, but I never said controllable set more. I have always been telling controllable space, because see, although it is a set, if I ask you, I give you a system and ask you which are the states which you can reach from 0, okay, you can give me a collection of all the state vectors which you can reach, okay. This is a set, but it turns out, and this is a subset of Rn, right, because we are only dealing with Rn. So, this is a subset of Rn. So, I can ask the question, is this subset a subspace also? Okay. It turns out yes, the controllable space is a vector space, it is a subspace, because we saw that controllable space is nothing but image of CAB or image of WT, the controllability Gramian, right, and we know that image of a matrix is a subspace, okay. So, controllable space is a subspace, whereas uncontrollable set is not a subspace. You take two uncontrollable state variables, you add them up, you might get a new variable which is controllable. The example that I have just now shown. So, as a whole, what have we seen? We have characterized which are the states we can reach from 0 in two ways. One is using the image of controllability Gramian and the other is image of controllability matrix. Advantage of controllability Gramian is that using the controllability Gramian, I can actually go ahead and create the input that will take you from 0 to that point. Okay. Whereas the advantage of the controllability matrix is that it helps us to easily check which are the places we can go. There is no time involved in that expression. It is just image of CAB, and CAB is this nice looking matrix BAB square B, a fat matrix. For CISO cases, this fat matrix becomes a square matrix. So, for CISO cases, single input, single output cases, we say that the system is controllable if the controllability matrix is invertible, because now it becomes a square matrix. I can talk about invertibility. But when it is a MIMO system, then the controllability matrix has dimension n into n into m, n into nm, right, and then it is a fat matrix. I cannot talk about invertibility of a fat matrix. So, we say that the rank of the matrix must be equal to n, okay, n being the number of rows, the rank of the matrix must be equal to the number of rows. Okay. So, this is how we understand, we have characterized controllability. This is how we can actually check whether a system is controllable or not. Physically, controllability is basically, the idea is to go from any arbitrary state to any arbitrary place. However, we have to convert this problem to a reachability problem, where we convert this problem to going from 0 to some arbitrary state, okay, because 0 to some arbitrary state is directly related to image of CAB and all that. Okay. I hope that this actually gives you an idea about what controllability is. In the next class, as we move forward, we will see how to use these ideas of controllability and uncontrollability to actually go for pole placement of the system or changing the desired pole locations. Remember, in PIDs we used to do this desired pole location business. So, that we will see how to change those poles, okay, using these modern ideas of state space and controllability, okay, and we will take it up in the next lecture. Thank you.